The big shift this week is that robot learning is moving from predict well to act safely, adapt online, and build reusable skills. One paper shows that low rollout error isn't enough if a predicted action can't physically exist. Another turns sparse success labels into usable credit for fine-tuning vision language action models. And a Berkeley system goes further, letting robots practice through self-directed play to grow a transferable skill library. Keep watching if you care about what actually makes robots reliable outside the lab. Let's explore the first paper. Can predicted dynamics exist in the physical world? This paper asks whether a predicted rollout, action chunk, or latent plan can be physically executable before execution, and argues that low prediction error is not enough. The contribution is a model-agnostic physical admissibility gate that decomposes executability into flow consistency, recursive reachability, bounded differential growth, and learned dynamics consistency, then rejects any decoded proposal whose worst normalized residual exceeds a threshold. The gate is evaluated on Hugging Face, LaRobot Push-T, using compact MLP world model baselines with a horizon of 32 and controlled falsification families, including smooth impulse, actuator lag, time warp, mode change, action state mismatch, and action saturation. On dynamic violation detection, the strongest scalar residual is the transition.rmse detector with AUC 0.982 and AP 0.997, followed by the standardized dynamics residual with AUC 0.972 and AP 0.995. Kinematic only scoring is much weaker at AUC 0.592, while the full admissibility gate reaches AUC 0.957 and AP 0.993 with condition level attribution. In replay intervention, the full physical gate prevents 87.7% of invalid proposals while causing 8.5% false interventions, and retained nominal progress stays near 0.998. The paper also shows that history condition prediction is more accurate than a state-only Markov ensemble on Push-T, with rollout RMSE 0.00221 versus 0.01, exposing partial observability in the monitored state and motivating runtime verification at the prediction control interface. Let's explore the second paper, Hierarchical Advantage Weighting for Online RL Fine-Tuning of VLAs from Sparse Episode Outcomes. Hierarchical Advantage Weighted Behavior Cloning, or HABI, is a new online RL fine-tuning method for vision language action models that targets a core bottleneck in robot post-training. Each rollout yields only a single success or failure label, yet the actor needs transition-level supervision. The paper from Ace Robotics, Tsinghua University, and the Chinese University of Hong Kong shows that a binary episode outcome actually contains two separable signals: viability, meaning whether a state can still lead to success, and efficiency, meaning whether a transition is moving toward faster completion. HABC trains a dual head critic, with a viability head supervised on all outcome-labeled policy execution windows and an efficiency head trained only on successful trajectories, then merges their one-step advantages with a state-adaptive gate that emphasizes viability when success is uncertain and shifts toward efficiency once viability is high. It also introduces intervention-aware credit assignment, labeling only the post-intervention policy execution suffix, so human corrections are not incorrectly credited or penalized. On 3 real robot bimanual deformable object tasks with a Pi 0.5 base model, HABC improves success from SFT baselines of 36%, 44%, and 12% to 92%, 88%, and 38%, while also reducing successful trajectory length by 55, 162, and 32 frames, respectively, showing both better recovery and more efficient completion. Let's explore the third paper, Playful Agentic Robot Learning. Playful Agentic Robot Learning introduces RAT-S, a multi-agent code as policy framework in which a robot does not wait for downstream instructions, but first engages in self-directed play to accumulate reusable skills. During play, a task proposer uses a Goldilocks novelty and learnability criterion to select exploratory manipulation goals, and an execution team writes, verifies, retries, and diagnoses robot programs before successful behaviors are distilled into a persistent skill library. The method is evaluated on Libero Pro and Momo spaces, where play-learned skills raise held-out success by 20.6 percentage points and 17 percentage points over CAP, Agent 0, respectively, while a random play baseline yields only marginal gains. The frozen library also transfers across environments. Plugging Libero Pro skills into CAP, Agent Zero improves RoboSuite by 8.9 points, and real-world manipulation by 8.8 points. And Momo Space's learned skills improve a separate real-world set from 3.3% to 25%. And Ablation shows that curiosity-driven play matters more than random exploration, and that playtime skill acquisition composes best with the full RAT-S verification loop rather than extra test time retries. The main technical contribution is a practical mechanism for converting autonomous interaction traces into named, reusable code skills for future manipulation tasks. That's a wrap on today's AI paper highlights. Thanks for watching.